Cool. But we're talking about the Super Bowl today. That started in January 2023, or at least the story around it. We had just wrapped up a week where everyone was on site for our like quote unquote quarterly planning. We don't really do much planning anymore, so it's funny to call it that. When we learned that the news, that like we had purchased a Super Bowl ad. It was the first time we were really finding out was when we happened to all be together anyway for these plans. That was top secret at the time, and the work involved, you're seeing this Project Daisy thing, you're like, what the heck is that? That's what we called it. We didn't want to necessarily have it leak, so everything was just referred to as Project Daisy. I still don't even know what this name means, so I can't explain it, but I do intend to get the origin story at some point, whoever invented this. I'm going to jump way forward to the end real quick. Sorry, the beginning's going to be a little bit back and forth, but I just want to really show how big of a hit this ad was. You're looking at the YouTube page comments for it. It was all just overwhelmingly positive. We saw the same thing on social media. It was nominated for awards. It was rated like the USA Today Ad Meter winner, which means that public sentiment was the most positive for this ad versus all other Super Bowl ads. Really, just to give extra context, it's obviously never good when the site crashes. It's really not good when you have a lot of traffic for a Super Bowl ad, but this would have been really embarrassing given like everything around this ad. So we didn't even know how bad it would have been, but we didn't want to mess it up. Hopefully that's clear. OK, but let's get to the tech part of it. I think that's what everybody's interested. This is what we had to deal with back in January 23 before we knew what this ad was or the actual event had happened. So this is really only the relevant portion of the system, I note. Highlighted in green is the things that are critical to the sign-up flow. Glossing over a ton here, but I think this is enough to give you kind of high-level context in order to do this talk. Also, I cannot even possibly start to describe all the tech that lives in these boxes, especially if you see this core monolith API. I don't know if anybody's worked in like a very fast-scaling startup before. There's like that old monolith. Everything just gets quickly thrown together. It's a big ball of mud. And then we have these things like the CRM and the fulfillment batch processes. Those are basically just like DDoS chaos machines breaking the thing all the time. Anyway, this is where we're starting from. But there's a big exception because we had, obviously as engineers, we want to make these things better, and we had already been pushing to like create some separation from this part of the system and like, hey, we have all of these things happening in the sign-up flow. We have to collect all the information from our customers. There's a lot of logic actually living before you are a user in our system. So if you see that box that's called TOSA, the totally optimized sign-up application, that's that application handling that portion of the user experience before you're a signed up customer. And it was really important we started doing this because it ended up being a huge help. The problem is, even though it's there as a box, it's like very in its early stages, like first iteration. So we hadn't quite decoupled all the things out of there that we want. Like it was still creating users in the main system the minute somebody like gave us their email address, weird things like that, that actually still created dependencies on the other part of the system and meant that it was brittle and the site could crash. Another thing, just to quickly get out of the way, there was just some like known knowns to this whole situation. We knew there were certain things we were going to do. We knew there were certain things we weren't going to do, just obvious stuff. So they're all listed here. Some of the stuff probably pretty clear to you already, like we couldn't refactor the whole system and make it loosely coupled in 3-4 weeks. But also maybe surprising, like we couldn't add a cache or a read replica. I'm not going to have time to get into the reasons why, but again, just talking about the tech debt of the way that monolith was set up, and it would create risk and bad user experience if we started messing with that data flow. All right, last jump. So this is when I'm going to introduce you resilience engineering, because like the thing about this is it's an awesome special event in that we were blindsided with the surprise. We had to scramble everything we could muster in terms of like our spare engineering capacity to deal with that surprise in hope of succeeding. And then at the end, we actually did succeed. It worked. But it wasn't like a crazy amount of traffic, right? Like big sites handle this amount of traffic probably on a daily basis. Well, the special is what we did in our system given the constraints that we had. And to me, that's resilience. And understanding and amplifying it, among other things, is what you might think of as resilience engineering. So that's the cool lens I'm hoping we can look at this event through for the talk. And maybe you can take that back to your own orgs, and it'll be helpful. But yes, first, let's talk about resilience, because people use this word a lot, and they mean all kinds of different things, and it's probably not what I'm talking about today. First and foremost, I think I see it interchangeably used with robustness a lot, and those are two kind of discrete things. Sometimes they're even in conflict, talk about in a moment. The drawing pictured here is by Lauren Hochstein. It's available at this intro post he has on an entire repo of resilience engineering resources. You can look that up right now. You can grab the slides later, but if you're going to go one place, or like if you're interested in this, you want to read some more, go to that post. It has everything. Lauren already did all the legwork for you. And from that post, it says a resilient organization simply is one that adapts effectively to surprise. No negative connotation. Doesn't have to be like a bad incident. Surprise, we adapt effectively. Keep that in mind. Robustness, on the other hand, is about how the system handles the known failure modes. So simple example, if you think about a robust system, is one that can maybe auto-scale if you get a traffic spike, at least if it's not a big Super Bowl traffic spike, if that works. You can think about that ahead of time. You create the auto-scaling. You have a more robust system. Yesterday, I got a good example. I think it was Joyce up here in her Ignite talked about the 6-hour Facebook outage. Also a really useful example for this, just from the standpoint, not because a deploy caused it, but because it was so prolonged, the engineers couldn't get into their own data center, which is really interesting, right? So what that tells me is that they were really robust to the specific failure mode of somebody like a malicious actor getting into their data center and doing something they're not supposed to. Extensive robustness, but it actually hurt their resilience, right? When they ended up in this surprise situation where they had this global outage, they didn't realize they were going to need to get in the data center. They weren't able to. So at times, just adding robustness to your system can actually reduce your resilience. This is why I think you need to understand the nuanced difference between them and make sure you're not making that trade-off unless you really want to. All right, cool. Another concept to introduce. So, a lot of the study around this comes from people that are researching and interested in how safety works in systems in general. And one of the important kind of concepts to call out here is like there's changing perspectives in this research. And the shorthand that's used is the safety 1 perspective versus safety 2. Without getting into all the details, I think like the diagram gets on the important part, is that the safety 1 perspective is more about that like simplistic robustness, something breaks, let's put in a fix, make sure it never happens again, kind of perspective. A lot of us probably still work in that manner a lot of the time. It's hard to get support not to work in that manner. But the problem with that is that if that's the only way you're creating safety in your system, that's a very small amount of the time and the events and the opportunities you have to create a safer system for you and your colleagues to work in. And like I said, the diagram shows it. There's all these other opportunities we could be creating safety or learning from. And safety 2 is taking that perspective of let's learn as much as we can all the time, all the everyday actions and outcomes. And then lastly, the reason I wanted to introduce this is because today we get to talk about something that isn't that typical, hey, here's an accident that didn't go as bad because someone intervened or it was a near miss or something like that. All those things are important and they're great and we should learn from them. But you don't really hear people doing talks like this where you get to talk about something where it went really good. Like things that are difficult but go right. So we got hit with a surprise. It was super challenging. We put in a ton of work. You'll see that in a minute. But in the end, it went right. We had a great outcome. The business was very happy with us. So I think that's great. I think it'd be great if we can do these stories more. OK, on to the next one. I know I'm throwing a ton of concepts very early on, but hopefully they'll all start to come together. I think it's needed. So there's this idea of boundaries as well. And luckily, there's a lot of visuals to support these explanations. Usually when we're talking about boundaries from a perspective of resilience engineering, people are talking about this Rasmussen model. It was introduced by a researcher named Jens Rasmussen. And it's nice from a couple perspectives, in my opinion. For one, it really makes it clear that a lot of the changes and the experiments we're doing in our system, they're not like secularly improving everything at once or inherently good. Like you're making trade-offs towards like potentially more risks that you're going to have a bad business outcome, or there's going to be an accident, or we're working harder like in this situation, and potentially people are going to be burned out at the end, and that's going to have anyway, these are all shown by these different boundaries, and you can imagine if it's like a point in here drifting towards them, that's showing how your risk profile is changing as you make changes in your system. And first quote of the day. Can everybody read this okay? I'm not going to read the quote unless it's helpful. All good? Yeah? In the back? Cool. So it's from David Woods. He's introducing this idea of resilience from the standpoint of something he calls graceful extensibility. And really, this is the first time I'm going to touch on this key point of adaptive capacity, your ability to adapt when needed. Do you have the capacity to adapt the system to handle a surprise? Okay, so let's talk workload boundary. This is my GitHub commits. I'm not like a green box person. I wouldn't show this for any other reason except this is like hard data on the amount of work that went into this. I think this is an extreme example. I hope it is, but there's a gradient. There are a lot of people, a lot of my colleagues worked really, really hard on this. Frankly, all of us put in a lot more work than we normally would have, and so you're probably thinking this is not a sustainable amount of work. Absolutely not. This would certainly lead to burnout for me and all of us over a long enough period of time. But in the short term, we could do that. We could risk that because you can rest before, you can rest after, take vacation over the summer. It's exactly what a lot of us did, and we were able to have that short burst of like stretching that extra capacity when we really needed it in those 4 weeks. And we were able to have good support from the business to not hit burnout later on. And I was debating even like doing this because it's like such a rough oversimplification, as I put. But if you imagine we were drifting around in that model, it's something like this, right? Like when we're in that starting phase, the system's not safe. We have that hairy monolith. But we're not having like bad accidents all the time either. So maybe we start off over towards that right side. When we're in the throes of the Super Bowl prep, now we are throwing a crazy amount of traffic at the system that it can't handle. So we are having accidents. You'll see we did have some outages, not when it was most important, but we did have accidents, and there was business risk to it. By the end, the system was much more scalable than when we started. So we were really at the lowest risk of having accidents at any point, but we were all pretty much burnt out because we had worked 4 weeks straight with no break. All right, getting back into the content of the talk. So let's talk about how we experience failure. So going in, like we knew we had this work cut out for us, but it wasn't really clear where the obstacles would lie that we would need to overcome. Fortunately, we were approached by stakeholders in the business, and they asked if we'd be ready in time to do earlier round playoff games. Our answer was no, absolutely not, but please buy those ad spots anyway because we need to practice in the real world data. This turned out to be like one of the most important things we did. We learned things from challenging ourselves and challenging the system in prod. We simply couldn't simulate with load tests in staging effectively or efficiently, or if we could, like, we were able to fold those things back in after we uncovered them in prod because it wasn't clear up front what we needed to do. And I don't know if everybody here gets to see charts like this every day or they know how to interpret them. But the clear thing you see from the top too is like the shape of that curve is really bad. Like that tells me that there's latency, there's probably retries, refresh. We have like this extended period of high traffic over many minutes versus the ones at the bottom. You can see the shape slowly starts to get better. Then plus in the middle too, you can see we're having error spikes, which is not good. But even as we're significantly increasing traffic, that spike is being handled much, much better as we move on. And so effectively, within the course of 2 weeks of testing things out in prod with these ad spots, we were able to more than like 10x the capacity of the system. Okay, so this comes from Richard Cook's paper, How Complex Systems Fails. Has anybody been exposed to that before? Read it? Yeah, classic, right? If you haven't read it, it's amazing. It's like a gateway drug for a lot of people into this content, I feel like, because it's so relatable. And it's amazing. Anyway, don't have time to really get into it. Point 18, though, is what you're looking at here, which is failure-free operations require experience with failure. And it goes on past what's on the page. This is where the system performance begins to deteriorate, becomes difficult to predict, or cannot be readily recovered. To me, I don't think I really called it out, but if you notice, there was 2 lines on the accident part of the Rasmussen model. I think it's called an error margin on that diagram. This edge of the envelope kind of aligns with that in my mind. I could be wrong on that. But I think the thing that's trying to be called out with that edge of the envelope is this is where it becomes like real when you're noticing like, okay, we're stretched towards the edge and we have some serious risk of accidents going on. You might start having small accidents, but the risk of this drastic degradation of system performance that Dr. Cook's talking about is at risk when you're getting to that point. All right, so I talked about adaptive capacity before. Another thing that's talked about is like this idea of being poised to adapt. So we already had a lot of adaptive capacity in the system. We were ready to muster it up, and I think one of the big reasons for that is the way we organize. So some background on that is that we have one integrated department referred to as Prodang, short for product and engineering. Prodang is further divided into pods, P-A-W, as in paw, dog pun. It's like a squad. We do that a lot. All pods build product, but the only differentiating factor between any of the pods are who the customer is. So if you're pod A, B, C, D, you're all essentially the same in terms of the activities you're doing, you just have different customers. And following that, the only difference between the platform pod and the product pods is that the platform pod builds product for engineering. So what do engineering teams need? What do our product pods need? They need all the things to build, run, and essentially all the factors of owning their own software. We believe in true ownership of the farmer's dog. There's no division of dev and ops. All pods develop and operate the services they own. You build it, you run it, taken to the logical extreme if you're familiar with that idea. So another little reference to get at the same point. This goes a little bit deeper on the adaptive capacity point earlier. And so organizing the product and platform, to say explicitly, helps us in two ways. It allows us to seamlessly reorganize around problems. Everybody's just an engineer, everybody does all the things, right? Doesn't mean everybody's the foremost expert on all the things, but there's no like, hey, that's not my job kind of thing going on. And it supports practices that directly provide capacity for us to adapt the software system. And I think let's talk about the second one first. We practice continuous deployment across the entire system at the Farmer's Dog. There's no single application that's not continuously deployed. And there's a reason for that. For us, it's just like an extension of ownership. If you think about if you have a lot of people making commits and you're batching them into deploy like once a week or something like that, who's responsible if something breaks in that deploy? It ends up being the ops team, right? So it doesn't really support the way we want to work. It can't be all those engineers unless you're going to create a team every time you do a deploy to run it. I guess maybe that is something you could do. But to us, the easier way to deal with this is just to have every single time an engineer makes a change for that to trigger a deploy, and then you know that engineer owns and is responsible for that deploy, and they should follow it into production. Without going through each one of these, in summary, these practices allow us to change our running software rapidly, safely, while aligning all engineers with how our software works in production. And it provides them the hands-on experience of working in production because it encourages them to go follow their code changes into that real-world environment. And so this provides the humans capacity to adapt the software, right? Because they are really getting into the weeds of understanding how their code is working for customers, and they can take that back and then iterate on it. And frankly, they can reorganize themselves around a wider range of potential problems, getting all of this experience with different parts of the system. So just to zoom in a minute on the deployment part in particular, this is like one of our typical CI/CD pipelines. They're always changing. It doesn't really look like this anymore, but this is from a few months ago. What is constantly true is that like it takes 5 to 10 minutes for any of our apps to end up in prod. And keeping that feedback loop short is what encourages engineers to follow it and to make sure things are working. The longer you have a gap between the time somebody commits their changes and it's like on main or however you're doing source control management, and the time it's in production, the more likely they're going to get tapped on the shoulder by a PM, another engineer, just pick up another ticket, whatever it is. The faster you can have that change actually take effect for your customers, the more likely the engineers on your team are going to get into production and actually follow along and make sure it's working right. I'm going to go back for 1 second. One other thing I wanted to touch on quickly, I think I have time. Just an example of this, right? Like, say this person who made this commit here is working on a team. Jessica talked about experimentation a little bit earlier. Imagine they're running a typical experiment, not really the subject of our talk, but like that A/B test that was mentioned. Perhaps they're trying to iterate on a feature. They're rolling it out to 10% of new users. This engineer made that, actually did these changes. So not making this commit yet, but is following along with the data in prod. They're seeing RUM data, maybe synthetic monitors, showing increased error rate that they weren't expecting that is related to that code change they made for this feature. Well, right here, this is resilience, right? It's a change, unexpected condition that was not foreseen by the designer. And now they're surprised by it. And how quickly can they adapt the system is the key thing, is what lends to resilience. Here, if you're using a feature flag, you're doing a progressive rollout, you turn it off, you try to understand what's causing that error, you come back, you can make this PR real quick, you get somebody to review it, then 5 minutes later, after you merge it, it's out on prod, you can flip that feature flag back on. So not only do we limit the impact of that potential negative outcome we didn't foresee, but we also create business value by very quickly correcting it and getting that experiment rolling again. So again, if you're in that weekly deploy process, it may not be able to go out for another week. You lose a week of that learning. You lose a week potentially if that experiment is going to cause a good outcome of getting that for the business. Last thing, just like this is our kind of deploy metrics. This is a little old. I saw like last week we did 150 deploys one day. But it's constantly moving up. I think the key thing I wanted to show here there is just like, hey, we deploy a lot. By keeping it fast and by keeping the feedback loop fast, deploying to prod continuously as a standard, we could scale up the amount of change a lot. Like, so there was a week where nobody was working. We were basically all off. There's no deploys happening. Nothing has to change. If there's a week, or I mean a day, where it's like I see some of these are showing like 10 deploys, we're not focused on like trying to deploy 100 times every day. If there's 20 changes that need to go out that day, that's fine. But when we do need to scale up, say it's 75, 80, 100 deploys, we can do that safely. Nobody has to do anything special. The system just handles it. It rolls everything out. Whether we're deploying 20 times a day or 100 times a day, the failure rate right now is less than 1 in 1,000. I don't have the exact number, but it's fractions of a percentage point. Cool. So these are all the things we had in place, and like this allowed us to change things really quick, right? We were poised to adapt the system because we had all these things in place. But that wasn't enough. We had 3 to 4 weeks to get ready for a Super Bowl ad, and a huge amount of traffic, the traffic you saw on the previous page. So we also had to adapt ourselves to gain even more capacity to make those changes using the adaptive capacity we had, if that makes sense. So there's like layers to this. It's kind of meta. Another quote from Dr. Woods and John Allspaw here, talking about this in particular. It's not only the ability just to make changes itself, but the system has to change how it works. It's models, plans, processes, and behaviors they're talking about. So let's talk about what we did there. Like I talked about, we found out about this at Q1 planning. Yeah, all that immediately got deprioritized, right? So no two ways around it. We had to focus on this first and foremost. Didn't mean we just like threw all those plans in the trash. Like people were still focused on other objectives that weren't working on this initiative, but it was very clear to everyone, like an ambulance coming down a busy road, like get out of the way for the Super Bowl, right? So the Super Bowl became the priority. It did take a little while to get this socialized though. Even though the other KRs and metrics were now supposed to be taking a back seat, like it was a change for the business to have something like this take effect, and we were like, we're gonna do this thing that might hurt a metric, and it was like, you shouldn't do that. So that was a challenge at first. We kind of saw this happening in engineering, gave the feedback up through leadership, which was really, really helpful in correcting this discrepancy. Maybe an unsuspected source of adaptive capacity where it said, hey, we're not getting buy-in for people to really treat this as the highest priority, came in, resolved that discrepancy, made it really clear to everyone in a fun way that, hey, it's cool, don't worry about the OKRs we talked about a few weeks ago. The Super Bowl is a success, we'll get back to that right after. Yeah, so the other thing kind of talk about is like we had to reconfigure ourselves. I think it kind of started getting into this with the platform and product part of it, that we had the ability to do that, but we didn't really do it as much to this point. But now we really were leaning into that. In order to solve this problem, everybody started doing different things than they were used to in their normal day-to-day. So myself and a few others started basically acting as PMs, as like senior software engineers. We set the priorities, picked which problems we would attack, make sure they were assigned to the right engineers that could go attack them. And our PMs really just helped us like with execution and make sure that got put into action. There are liaisons with stakeholders, really pushing when we like maybe we're going to take a risk and make sure that was okay, making sure that we had good kind of fallbacks for that. And then I guess even like we were talking about like Scrum Masters, it's just making sure that people were able to do the work, weren't blocked, focus on execution in that sense. And anyone working on these initiatives joined a daily stand-up. So every day we could make a tweak or an adjustment if needed. We could switch people. And we prioritized getting things out to prod as quickly as possible. Like we made an intentional choice to be less thorough normally than we would, because if you have an accident 2 weeks before the Super Bowl, when you're not really doing a lot of advertising, it's a lot better than having an outage during the Super Bowl ad. So yeah, we pushed things out way faster than we would have under normal circumstances, weren't as careful. And we actually did have 8 small outages on the scale of seconds to minutes during this time, but we didn't have one during the Super Bowl, so that's all that mattered. Unless we touched on, I think maybe someone touched on mob programming yesterday. It's up there. Like we did a lot of ensemble mob programming, people jumping on Zoom with each other, throwing a code editor up, and having like 2, 3, 4 people working on things at once. That was great from a speed factor, and that we had this just one thing we need to get done, because a lot of time gets spent waiting for Slack replies or PR reviews, stuff like that. It just doesn't happen when everybody's working on the same thing together. Okay, quick intro before I play this video. So there's a term for the thing I talked about, the reconfiguration. I saw a similar example in Laura McGuire's QCon talk. She had a video of LeBron. She used to explain this concept. She told to me when I told her this story, which is that of dynamic reconfiguration. It's this ability where when there's a goal in the system, that the actors within it can reconfigure on the fly as needed to make sure you reach that goal. And I know basketball's probably not the best metaphor for everybody. If you're not a sports fan, I'm sorry about that. I don't think you really need to know the sports because you can just see it visually. But the goal of playing defense on basketball, you don't want the team to put the ball in the net. That means you have to guard all the different people and make sure the person with the ball doesn't have an easy path to the basket. So I think this really, just to play off Laura's example with LeBron using NBA defense, I couldn't think of a better visual for this. Yeah, so see how everybody's sliding over if an offensive player gets some space and ends up open. It's not that person that's playing man-to-man defense on them. Like usually one player will guard another player consistently until there is that defensive breakdown. Then everybody starts to shift and rotate and help each other. And that's dynamic reconfiguration in a nutshell to me based on the way I understood it. And just to go a little bit deeper into this basketball metaphor, another really good visual. It's really clear why this has happened, because the NBA, like professional basketball, has changed so much in the last like 20, 30 years even. All the players now stand around the three-point line and they're taking shots further and further away. So what does that mean? That there's way more space for all the other players to run around, run screens, try to lose a defender, do way more complex movements and actions. So what we've seen in professional basketball is with that increasing complexity of all the different offensive schemes that can be used because there's so much more space, is that defensive versatility has become a major, major premium. Can somebody play on defense 3 or 4 positions even, maybe guard 1 through 5? That's a really, really in-demand skill right now in the NBA. And I think there's kind of a similar thing happening in software engineering to some extent. We talk about shift to platform engineering, what we're doing with platform and product. In some businesses, it doesn't apply to every business, obviously, but in a lot of cases, at least the type of work we do, that makes a lot of sense because the complexity has increased so much. We know everything from low-level React, CSS and JS stuff, all the way down to Kubernetes, Docker, the VMs are hosted on, the cloud providers, how all that stuff works together. It's just a massive surface area, right, of complexity. It's more problem space, just like the NBA has with its defense. Last visual to really make this clear. Not sure if it's clear for everybody in the back, but you can see the 1990 shot, how everybody's just kind of standing in the paint. It's not really a big deal if you lose your guy because there's somebody else standing right there. It's not like they have an open shot. Versus your local Denver Nuggets, look at Nikola Jokic where he's standing, all the way up near like center court. And this is the center that used to just stand under the basket. Now you have this 7-foot guy out near the center of the court that can pass, shoot a three. How do you defend that? It's so much harder than it was. All right, on to reciprocity. So when I talked about stakeholders giving up their OKRs, that was a small example of this, of reciprocity. In the short term, they made a sacrifice on their goals, what they wanted to accomplish, for this larger goal of making the Super Bowl a success. And we had to ask them to make that trade for us. Basically, nothing in the short term was going to benefit them by doing this. They just had to trust us and give us some of their capacity now, and we could hopefully make it up to them later. One of our values at TFD, I think, really helps support this is called Play Team. Blurb up there, but I'll read part of it from our values guide. To play team, first and foremost, means that we all share the same goal. We take individual ownership and hold ourselves accountable for the success of the entire team. Truly being a team player means that each of us needs to carry our own weight. We make sure others can rely on us. And I think the really important part to this is the second piece is that when we do need help, we don't hide it. We ask for it, and we get in there and help. We should pitch in or fill in gaps when we see them. Okay, sorry, if you were just like, I just want to know what you fixed, tell me the tech problems. We're getting into that now. So thanks for sticking with me through all that. First thing, I think this was like literally the first thing we encountered. So we're mostly a node shop. I don't know if I covered that. Almost all of our software, even the backend software, is JavaScript. That has its own basket of problems and pain and suffering. But one of them just tends to be like node modules in general. They're very big. But then also, a lot of them are just questionable. So the AWS JS SDK had one of these questionable defaults. They ended up fixing it in v3, so it's not like this anymore. If you're using v3, you don't have to run back and like say, oh, no, oh my God, is this going to happen to me? It's only in the v2 version of the SDK. But we were just running out of sockets. We didn't understand why we were hitting latencies on DynamoDB. We used on-demand mode. Didn't make any sense. But then we realized there was no keep alive, and we were being limited to 50 TCP sockets. So that was our max concurrency to the database, even though we needed a lot more than that. After further inspection, it kind of like lit off a light bulb, like, aha, if this is happening with Amazon, it's probably happening in other packages too. And we did find a bunch of these kind of like networking tweaks we needed to make sure things could handle the scale. Another big one we faced, has anyone run out of IPs with Kubernetes on AWS before? Yeah, it's a pretty common one, right? Yeah, so our Kubernetes cluster used up all the IP addresses in our VPC. Why? Because Kubernetes uses a lot of IP addresses. We had just never encountered this before. And even doing load tests, we didn't encounter this because like what happens with staging, right? Like things are matched, but they're not scaled up all the way. Maybe somebody has a random thing in production and doesn't really have a staging environment that's using IP addresses. So we actually were utilizing a lot more IPs in prod that weren't for Kubernetes itself than in staging. So this is something we just had to run into. I think it happened the first game. We scaled way higher than we needed to, so it didn't cause a problem. But that launched us on a major project to essentially migrate our whole Kubernetes cluster. This is also a good example of the parallel change pattern. So when we did this cluster migration, we always do it. We deploy a brand new cluster. We make sure it's stateless so we can do this. And then we slowly migrate the apps one at a time using like an edge load balancer to distribute the traffic so we can test like 10% of traffic on the app on the new cluster. If anything goes wrong, we just roll it back. We just send it back to the old cluster. And then we leave it around for a good while after, just in case there's some kind of latent thing. All right, last one I'll note is Postgres' trouble with connections. If you use Postgres, you probably run into this before. So this is a funny one. Like it's something I've hit many times in my career, but probably not for the last 6 to 7 years prior to this. I think just kind of like the shift towards working more in startups and then microservices. For an individual service using a Postgres database, you may not hit this limit, but we hit it very quickly now with this level of traffic where we had a CPU-constrained workload, and standing up the connections on Postgres is very CPU-intensive. So what you can do is use something like PG Bouncer. Actually, I'd say that's preferred if you're using JavaScript, because another quirk of the libraries is that they send settings on the client connections that make RDS proxy don't work. So if you're using something like Sequelize or anything based on connects, pretty much, like don't bother with RDS proxy, it's not going to work. It's going to not let you multiplex those connections. PG Bouncer does work though. We use this Docker container I linked. If you're interested in learning more about that, if this is new to you, there's a link on the slide. You can grab it later. So we couldn't fix everything, right? But we still need more capacity. So what can we turn off to, basically shed some load and give capacity back to the core part of the system for this event, which was the sign-up flow? A big this is a big part of the tech that I said I want to get into, but here's an example of something we had to deal with. Somebody had decided early on, probably for good reasons, in that like, hey, if you load the customer account, all your subsequent actions will be very low latency if we preload a bunch of stuff into the browser for you. The problem with that is it was like too widespread into everything and deeply ingrained in the system for us to be able to like rip it out. So even though this had a particular purpose under some kind of assumption that we weren't going to need to optimize for like this kind of scale, at this point was no longer useful for us, and we couldn't take it out. So we just created like a block list of queries and mutations that didn't depend on it for one to bypass it, and then as you'll see later on, we turned off the whole customer account so it wouldn't do that at all. Another one we had to turn off, this audit log. I feel like that's kind of loaded. That can mean a lot of things. For us, it's not an audit log at all. It's essentially, I would describe it as a custom implemented transaction log living in our application code. So if you're familiar with Postgres, it has this implementation of a wall log, which is its SQL version of transaction log. MySQL has its own. So you might already be thinking like, well, why did you write your own if it's already in the database? Can't answer that question. Again, someone did this a long time ago. They probably just didn't know they could hook into the wall log and get those transactions from that. But it was super harmful for a number of reasons, right? Because like, it's unnecessarily creating extra write to this database, which is now like a single point of failure and a bottleneck for our sign-up flow. The table itself is a coupling point, because every time a transaction happens to multiple tables, now they both need to concurrently make a transactional write to this same audit log table in the transaction, which is going to create crazy locking things. And then lastly, the implementation itself, the reason that code is up there is because Sequelize implements a function that we use to implement this audit log thing, uses a sub-transaction. It uses this temporary function, which is kind of a wonky way to do a sub-transaction. If you're familiar with SQL, the way you normally do it is a save point. It's like you have if you do a transaction and you can roll back to a certain point, that's a nested transaction or a sub-transaction. But yeah, Postgres cannot handle those. A lot of people have learned this the hard way. I think, next slide. Here's at least 3 incidents involving sub-transactions. Sentry, GitLab, and even Amazon can have mishaps with new tools going from Oracle to Postgres. And there's a nice overview of this Postgres AI blog post. If you're not familiar with that and you're like, well, I want to make my database more performant, get more out of my Postgres database, you can see if you have any sub-transactions hanging around, because they definitely do a lot of harm. All right, coming back to that initial diagram. So going through all those things we did, this is pretty much what it looked like at the end. The red X's, like those are all the things we just turned off. I think even like the landing page itself, we put up a different version of it that was extremely static and had no functionality versus the other one. So like our normal landing page was technically off, customer count off, CRM off. We could not serve CX requests. All those batch processes were turned off. We just cleared the way for everything in the green in the sign-up flow. So our 5-minute sustained load test, after doing all of those fixes, shedding as much load as we could, we were serving 3,000 requests per second, which massive improvement even over that first game which was 100 something. We'd already done prep before then. We could have probably gone higher than that and handled it very easily, but we were confident this is more than enough capacity for the Super Bowl at this point, so we rolled with it. But we were not done, because even though we had tested all this stuff, it all could have, we knew we could handle the load, never know what's going to pop up in production, right? Like, still wanted to be prepared for an unexpected surprise, even though we covered all of our bases, right? That resilience principle. So just in case we messed something up, something went wrong we could not foresee, we had waiting rooms, fallbacks, things like that for every part of the system that was still online. So we could provide the best user experience possible for people that might see the ad and still come to the site. And then, you know, if they wanted to leave their email address, we get back to them later and let them know when it's back up or get them signed up manually. This is the ad. I'm going to just skip. But if you want to grab the slides and watch it, you can. Otherwise, it's on YouTube. OK, so let's talk about the overall lasting impact of this. I think for one, we're much more willing to try things now after we did all that dynamic reconfiguration. And people were totally out of position doing what needed to be done to you know, solve this problem of the Super Bowl. So for one, there's like the defined experiments with our process I think are good. And then also, we just do that dynamic reconfiguration thing more, where somebody sees a problem, they assemble a team that is needed to go solve it, and they go do it. And that's just an accepted way of working now at TFD. Also, engineering itself, I think, built a lot of trust. There's a lot more reciprocity with engineering in terms of us getting capacity when we needed to solve our problems and to hit our goals. So that auto log thing I talked about, that was so deeply ingrained into the system. Almost 2 years later, we're like really, really close to deleting all that data, the whole thing, removing it from the system. Took a lot of hard work from a lot of people over a long time, and you know, I think the Super Bowl directly led to that. And then lastly, you know, I talked about before, you got to be careful. When you're adding robustness to your system, you can reduce resilience. And I gave the Facebook example. Someone also had a good thing yesterday that leads into this, talking about like, hey, I got a ton of noisy monitors. How do I fix that? And not to get into how to fix that, but you know, the light bulb went off when somebody proposed that open space. You see that happen a lot when somebody's kind of going through, you know, an incident review template, and it's just those kind of robustness type fixes. Like, did you add a test? Add a new monitor. Well, what do you end up with? You end up with a bunch of noisy monitors that aren't really giving you good feedback or data, and then that can create alert fatigue and actually make you less resilient overall. So I think we do a really good job of this. It's really fun to work with my colleagues and get to work with a group of people that, you know, they think about things like, well, if we needed to do another Super Bowl event, would this make it harder or not? Not even just in terms of traffic, but if we had to scramble for a surprise to seize an opportunity, making this change for robustness actually make it harder to do that. All right, and that's it. I just want to say thank you all for, you know, taking the time.